Okay, chapter 4 of Pearson Basic Chemistry. We're going to look at elements and symbols, the periodic table, the atoms, atomic number and mass number, isotopes, and atomic mass. There you have it. You're going to note the mass number versus atomic mass. Okay, it's what you're going to hear us talk about, right? All right? Is everybody with us? So we're going to talk about these concepts. And we're going to move at a pretty good pace. We've already gone through one work session on this. Therefore, when we get to those parts, we're going to whiz right through it. And the things we don't cover in the lecture, we're going to go back to another session. Everybody follow how we're doing that? All right, let's get going. Elements are pure substance from which everything else is built. Voila! The periodic table is composed of pure substance. All right? Keep that in mind. That is the bottom line. So your periodic table, and you're going to learn most of your chemistry from the periodic table we will be referring to, so you want to have one ready to go. Chemical symbols are one or two letter abbreviations for the elements they name. You know this already, but we're emphasizing it. Be careful when you write these. For example, lithium is uppercase L, lowercase I. It is not two caps. If you do that, it's going to be wrong. Okay? You can't write chloride, a chloride ion or chlorine as Cl. It has to be as a lowercase c and uppercase L. It has to be uppercase then lowercase. Zero follow. It has to be exact. There are no exceptions. I make no exceptions for that. And I won't apologize for taking all your points just on that one stickler. Okay? Why is that important? If you're going to be giving grandma her meds, you want to know exactly what they are. Okay? You don't want to be close. You want to be exact. All right, so keep that in mind. So here we have cobalt versus carbon monoxide. But carbon monoxide, by the way, is called the silent killer. If you suspect carbon monoxide, leave the area. You cannot hold your breath long enough to survive it. It is a dangerous thing to do to go in carbon monoxide area. Don't second guess it. If you suspect carbon monoxide, leave the area and let the pros take care of it. Don't try to be a hero and go back in and save your little dog. You might not make it back out. It is that deadly. You don't know when it gets you. Okay? This is just examples of showing you aluminum, silver, gold, and sulfur. I will expect you to start to knowing some of these. I do not expect you to memorize the entire periodic table, but I certainly expect you to know carbon. I definitely expect you to know silicon. That's the metal that's used in your cell phones. And some of these others, as we go, I will expect you to know them. And I will be, for example, I might say sulfur, and I expect you to know that. Okay? Toxicity of mercury. Mercury's example is it's a very toxic material. Mercury can enter the body through inhaled mercury vapors, contact with the skin, ingestion of food. Mercury is really harmful. In the body, mercury destroys proteins and disrupts cell function. It short circuits your cell functions. It's like putting a short circuit material in there, and it's kind of shocking you, and it just won't let things function properly. Long-term exposure to mercury can cause brain and kidney damage, retardation, and decreased physical development. Mercury is a silvery, shiny element that is a liquid at room temperature. If you have mercury thermometers in your home, it might be to call Consumers Power or whoever, and they will usually take them out free of charge for you. Okay? All right? So be aware of that. So the point here is that the materials, the elements on the periodic table have different form. They come in different forms. Note the following. This is important to note that group 17, called the halogens, are diatomic. Okay? Keep that in mind. They are diatomic, meaning that we don't write them as F. We write as F sub 2. Chlorine in its natural state is not Cl, it's Cl sub 2. So everyone understand that. Bromine is not Br in its natural state, it is Br sub 2. That's what we mean by a diatomic. Does everyone follow that? We got that? Do I need to write it? We're okay?
Will you write it, please?
Okay. Yes. So fluorine is F sub 2.
Okay.
Got it? Cl, that's my C and that's an L, that's the best I can do, is that. Okay?
And that's the entire line of 17.
That is correct. That is correct. Br. In addition, oxygen in its natural state is O2. Nitrogen in its natural state is N2. These are called diatomic. atomics. Okay? In their natural state, they exist in and it's a dimer. Okay? And so we have what? 2 atoms of nitrogen, right? Now, when we talk about elements in chemistry, chemists are a little right-handed, and they're a little backward. So we read from right-handed back in terms of the 2. The 2 refers to the thing that's in front of it, not after. You get it? So N2 tells me I have 2. So we write here, up. That's how chemists do it. Okay? That is a convention. That won't change. Someone asked me in one lecture, why did they write it different? I don't know. I wasn't there when they thought of it. If I thought I might have written it completely different. Wasn't my idea. But this is the convention. This is the acceptable form when we write these. And you'll want to get used to that. Okay? That's how we write it. So 2 atoms, 2 2s. These are all diatomic. And on the periodic table, all of group 17 is that. And we have nitrogen and oxygen that joins the band. This just tells you who discovered it. It's okay if you memorize Dimitri as discovering it. That's okay. I rarely test you on who discovered it. Okay? So it arranges the elements with similar properties, and I think you intuitively know that. If you've taken high school chemistry, you're aware of that. They have similar properties. Now let's start talking about those similar properties. You're going to see it repeated in this lecture. We have rows and we have columns on the periodic table, and you see that on the periodic tables, right? If it's in the same column, then the similar properties run down the column. If it's in a row, then it will have some properties that are alike run across the rows. It's that straightforward. Okay? There are properties that are shared based on where it is. When it's across the rows, the shared property tends to be the form of its energy. Okay? And that changes as we go across from right to left, and you're going to learn all of that. When it goes up and down, essentially the chemistry tends to be quite similar. Does everyone follow? So it tends to be rows tend to be the energetics or the energy, and the column tends to be the type of chemistry that undergoes, and that's what we're showing you here on this periodic table. So we have 18. For this class, I am comfortable with us memorizing 1 through 18. Okay? So we have 18 as we go here, and we have 7. This is a grid. That's it. These are addresses. These are IP codes. Okay? Does everyone follow? So when you look at the periodic table, don't just look at it as a bunch of things there. It is an organized address book. Here, beryllium is in what? Group 2, row 2. You get it? Does everyone see how that works? These are all addresses. They're IP addresses, like your cell phone. It has a unique IP address. So here, boron is in group 13, row what?
2.
Row 2. You get it? Yep. These are all addresses. Does everyone follow? That's the periodic table. That's how it's organized. Okay? And when they're all in the same row, the same column, apologize, when in the same column, they have similar chemistry. So chlorine has similar chemistry, fluorine, boron, etc. Okay? Because they're all in the same column. When we go across here, it's related by energy. But that energy shifts as we go from right to left. Does everyone follow? Okay? So when you look at the periodic table, you look at the unique addresses of each of these. This is row 3, group 2, etc., etc. Notice here we don't have anything. These are vacant, and you'll learn why. Okay? These are our IP addresses. We're gonna narrow these IP addresses down to being more specific of what type of address they have. Where are they located? Okay? They're basically folders or basically, again, addresses on the periodic table. You're going to learn more about what they are. So everybody with me so far? Okay, so we have columns, similar chemistry, and we have rows that deal with energy. Each of these are located at a very specific address. And note they have the protons. They have the atomic number, okay, which represents the number of protons, which for neutral elements also represent the number of electrons. Okay? And then we don't have one here. So this is what we have. Then each of the, okay? Now, we also have metals. So we have more metals on the periodic table than we do anything else. Note that because I asked that kind of a question. The periodic table is composed mostly of metals. Then we have metalloids. This is a cell phone. This is electronics. Metalloids are used in electronics. Okay? So we silicon, we use the other one that's used actually is phosphorus is used. So because it's adjacent. So we have metalloids, and then we have the nonmetals. Hydrogen kind of tends to be a nonmetal, and so it's written here in yellow in this one. So yellow, nonmetals, green, metalloids, and the blue or purple, these are your metals. So that's what your periodic table looks like. Here we repeat, elements arranged according to similar properties in the vertical columns or groups. Periods or horizontal rows of elements. And this deals with the energy, and the energy shifts from left to right. And so here we show you these examples. Here, again to repeat, these are the addresses. Get it? These locations. It's like reading a map, like reading a grid, like reading graph paper. Okay? So don't look at it as being, just simply look at where do you want to be. What's the address? Okay? So everyone follow. Okay? So don't sweat it. Just read it. Group numbers, we just talked about already, right? You get it? You have how many? 18 group numbers. And that's how we're going to talk about them, group 1 through 18. The subcategories are these. The analytical chemists use them a lot. And they do have, these notations suggest the types of chemistries, but we won't in Chem 150 be going to that level. So we'll be using simply the numbers, 1 through 18. Okay? Here, we show you the families of these. We have the alkali metals, alkali earth metals. Then we have transition elements. And these are metals also. So here, these are transition, meaning that they are somewhat schizophrenic. It depends on how they're used and who they combine with what they will be. They will one day, iron will react with oxygen in this fashion, and the next day it combines with oxygen in another fashion. Transitional. Has different charges, different energetics, different valence states. Okay? Here we have, let's say no common names, there really aren't. Here, you have the nonmetals, and you have, again, the metalloids. But here we have the halogens, and what do we know about the halogens? They are what? Diatomic, right? In their natural state, they exist with a sub 2. And then we have the noble gases. The noble gases are gases because they have fulfilled, note this, the octet rule. They have 8 electrons around them, and they wish not to be bothered. Okay? So they're used simply as gases. Okay? Right? They don't like to interact in terms of do chemistry or anything. They just like to bounce around. Okay? They are free-spirited. Okay? Because they have fulfilled their noble quest for 8 electrons. And in fact, they recognize also that the elements on the periodic table undergo oxidation and reduction to try to fulfill to reach their noble state. These are noble, the rest of the world is not. They seek to do that by oxidation and reduction. Here we show you some examples of these. Again, we won't go into any detail. These are just examples here. Alkali metals. Okay? Then we have the alkali earth metals next to them. We have the halogens. When alkali metals combine with halogens, they form salts. Okay? So alkali metals combine with halogens, they form salts. Sodium chloride is the example. So we form salts from reactions of alkali metals with halogens. And we get these salts. It's because one side of the table wants to be oxidized and the other wants to be reduced. And therefore, they make a really good partnership We show you here the diatomics, and we show you here they react and they form these really nice compounds. Here, these are used in the electronic industry, cell phones, iPads, televisions. These are called metalloids along the diagonal, periodic table diagonal. Pace is okay? Here, most metals are shiny. You know that. Ductile means they can be shaped into wires, which is why we like to use copper. Here we can hammer out gold and mold it and put it in your mouth and make a grill. Oh, yeah. Okay, I'm sorry. Too much fun. All right, so there you have it. Good conductors of electricity. Why is it a good conductor of electricity? Electricity is the 3D flow of electrons. So when electricity flows, it's actually 3D. It's running along. You have these electrons, and you know what electrons are now, right? Yeah, because we were already going through that in our work session, and we're going to talk about it again. These electrons, they run in a 3D fashion along the wires. They come from the power plant, and they go to a transformer. Transformer gives them more juice, and they pick it up again, and they come through Davenport University, and they run into some interferences, and those interferences start to glow or excite. Glow if it's a basic incandescent bulb. If it's fluorescent, it seems to excite the molecules. The molecules get excited, and they shine as light. Get it? So electrons hit the wires, and it goes to a high excited state and releases itself as light. In the case of incandescent, it's saying, I can't get through there, so it glows really hot. That's why it does it. That's why incandescents are cool light, because they simply get excited and smile about it. Incandescents get hot because the electrons are trying to get through there, and they can't get through at the pace, and they glow. That's why, and we use metals to do that from the periodic table. Solids are room temperature except for mercury. We've already talked about mercury. Here are the metalloids. We won't talk much about it, but I expect you to know silicon is the leading metalloid that you should know about. Silicon. That's the metal of your cell phones. That's what's made out of Hemlock Semiconductor in Hemlock, Michigan. They're still one of the world's leading suppliers of that material. Nonmetals, we talked about these already. Carbon is one that I expect you to know, right? Carbon, nitrogen, oxygen, chlorine, etc. Carbon, hydrogen, and oxygen are the source of life for us. Photosynthesis is the reaction that allows life to be generated. Gives you green plants, gives you organic matter and organic life. We have chlorine. Then we have the nonmetals. They're shiny. I expect you to know some of the properties of these. Only 20 elements are essential for well-being and survival of the human body. Okay? So be aware of that. Only 4, oxygen, carbon, hydrogen, and nitrogen, make up 96% of the body mass. That's it. You have a little bit of phosphorus thrown in there for ATP, things of that nature. Okay, which is used for the ATP, used for your energy generation. It helps with your enzymatic processes. And then we have these minerals that are essential. This is why occasionally you see the animals out licking the ground and things. Here, typical amounts of essential materials here. I don't expect to memorize this, but I think it's something good for you to be familiar with and just kind of study over and read. Here, same thing here. I don't expect you to memorize all these, but we kind of would like for you to at least be familiar with it and just give you an idea of what's needed and what's there. And this is why you kind of learn this from dietitians. Dietitians are very, very good at talking about these types of things here. So be aware of that. Here, we show you the minerals. These are some important essential minerals here that your body needs, and they're all on the periodic table. These are the major elements there. And then we have these micro minerals, phosphorus, sulfur, and chlorine that your body kind of needs depending on where it is. Okay? Be aware of those. So that brings us now to talking about the atom. Now we've already gone through a work session, right, to introduce you to atoms and what atoms are. We've already introduced you to how to use them, how to count them. So we're going to go through this to reinforce what we've already talked to you about in the session offline. Right? Ready to go? So this you're already familiar with. Let's go through it. Watch. All elements listed on the periodic table are made up of atoms. Atoms are the smallest particle of an element. There you go. The smallest particle of an element, I expect you to know that definition, atom. Atoms are the building blocks of everything around you. Too small to see with the naked eye. The building block, you are atomic. Okay? You get it? This was developed, the theories of this were called by John Dalton. He developed the theory. So the bottom line is we're made up of atoms. That's what you need to know. All matter is made up of a tiny particle called atoms. All atoms give elements an identical, all atoms of a given element are identical to one another and differ from atoms of another element. In other words, when you get oxygen, oxygen atoms are oxygen atoms. Okay, does everyone understand that? Nitrogen atoms are nitrogen atoms. Okay? Sodium atoms are sodium atoms. They are not confused about that. Sodium knows it is not magnesium. Okay? Sodium knows it's not potassium. Okay? Everybody follow. That's important. Atoms of two or more different elements combine to form compounds. So we have atoms. Atoms make compounds. Compound makes matter. Matter that we can see. We can't see the atoms. The atoms become compounds. The compounds grow matter, and it becomes visible. You're going to be learning later about how we see things from the electromagnetic spectrum. We're all good? Pace is still okay. A chemical reaction involves the rearrangement and separation and combination of atoms. This is important. When we carry out chemistry, nitrogen has some atoms, and those atoms will get blown to smithereens, and it would intersect with some other atoms that intersects. Oxygen has been blown to smithereens. They recombine, and you get nitrogen oxide. NOx, which is the brown stuff, smog. Okay? You take hydrogen that's floating around, and you have oxygen floating around. And hydrogen is diatomic, by the way, also. And oxygen is floating around diatomic. The diatomic hydrogen blows to smithereens. Oxygen blows to smithereens. They react with each other, and they recombine and form water. Get it? That's what happens to elements. That's how we have the compound. So water builds up, and it becomes an ocean. Okay? Or a lake if you're in Michigan. Guy by the name of Rutherford, he kind of discovered something. He said, you know what? These atoms aren't just atoms. He discovered through an experiment that there are some smaller particles, the particles that we already talked about in the earlier session, right? What are they? Protons, neutrons, electrons. These are the subatomic particles that you want to know about. Protons, neutrons, electrons, which you now know because you've already worked through them. That's what he discovered. And he discovered that these protons are positively charged, neutrons are neutral, and electrons are negative. Okay? The primary character of all elements comes from its protons. Note that. That is where we get the primary character of all the elements. That's why their atomic numbers are listed as they are on the periodic table, because those are the number of protons. The primary character of all elements is its number of protons, its atomic number. So if you know the atomic number, you know the primary characteristic of oxygen is different than of fluorine because it has different number of protons. Okay? So the primary character is protons. Okay? The size and volume or size of atoms is based on its electrons. So electrons contribute to size. This is going to repeat in a few slides, but I want to go over it now, and then we'll walk right through those slides. So size is electrons. You get it? Volume. If you want to know the size, we think electrons. You want to think its primary character, you think protons. If you think it's mass, then you involve protons and neutrons. Everyone follow? Protons and neutrons, you think mass. If the mass is going to vary, it varies by neutrons. That is a term, write this down, called isotope. I-S-O-T-O-P-E. I-S-O-T-O-P-E. That varying of neutrons is called isotope. So you can have several neutrons, but you can only have what? Proton is set. That is the base characteristic. Protons do not change. Electrons can change. Neutrons can change. But for Chem 150, we're going to limit that the electrons here will be based on neutral species, except for the homework assignments. You have to do those like they are. Okay? So, we know a lot now, don't we? A lot about this. We have subatomic particles. What are they? Protons, neutrons, electrons. Protons are positive. They contribute to mass. Neutrons are neutral. They contribute to mass. Electrons are negative. They contribute to size. Okay. Protons plus neutrons gives you the mass number, or atomic mass. Okay? You'll hear that interchange. Atomic mass, mass number. Same thing. Neutrons can vary. When they vary, it's called isotope. When they vary. Okay? So everyone follow that. Do protons ever change? No. They're always atomic number. That's what this is about. Small region in the center makes up the nucleus. The nucleus is composed of protons and neutrons. So nucleus is what contributes to the mass. The mass is in the nucleus because that's where the protons and neutrons are. Okay? The electrons are spinning around the outside of the nucleus. Okay? That makes up the size. And, watch this. You ready? Depending on what row they are in, tells you the size. Row 1 has 1 ring. Row 2 has 2 rings of electrons. Row 3 has 3 rings of electrons. Row 4, 4 rings. You get it? So, cesium has a larger size than what? Sodium. Does everyone follow? So this is like building your own private planet or universe, right? So this here has this two rings. This has 3. You get it? And it goes on and on down to here. So I can ask you already which of these has a larger size. Iodine has a larger size than chlorine, doesn't it? Because you're just simply reading it. You're not memorizing it. You're just counting down. The size of rings on iodine is the same, well, let's say, right, as rhodium or any of these others because we're 5s. You get it? So everyone follow that. So there you're learning all from the periodic table about size. So these are large. So size, atomic radius, increases this way because it has more electron rings around it. And it has more electrons. Okay? Is everyone with me? All right. We're going to learn more about that. So he discovered that. So the region of space, we just talked about, right? These electrons. This is size. If an atom were the size of a football field stadium, the nucleus would be the size of a golf ball. Let's just give you an idea. So if you had U of M stadium, you put a golf ball in the center, that's about what we're looking at. Yeah. You get it? The nucleus is right there in the center, and the electrons are the spinning rows in the stadium. And look at that. That nucleus in itself has the most mass. But the size is by the electrons. Does everyone follow that? All right? So that kind of helps you to get a real vivid picture of what we're talking about here. And so those rings, what row are you in? This is the nosebleed section. You get it? And so here you're right down here on the field now, baby. Okay? These are the $5,000 seats. These you can get for $1.50. Okay? So everyone understand it? That's what's happening. That's what electrons look like. This is the whole thing. So this is what's happening. It kind of looks like a small, so when next time you look at kind of the star, this kind of looks like its own small universe, its own small planet. That's what we're looking at there. And we have the positives, the negatives, and the neutrals. To give it its protons by its character, neutrons give it its, help give it mass, electron gives it its size. The mass is due to protons and neutrons. We've already talked about that. Okay? Chemists use a unit called atomic mass, AMU, to define, this atomic mass unit, that's the number you see on the periodic table. The atomic mass, or the mass unit, is the whole number. Does everyone get it? We're going to come back and talk about that a little bit later, so we won't stay on that point. Okay? We'll come back to that later. Does everyone follow? Okay? Because I don't want to confuse it. And here we show you a summary of what we've been talking about. Look at it. Protons, they're plus charge. Remember we said that? We said what? Neutrons are neutral. And we said electrons are what? Negative. And this is why the mass. You now know how to deal with this when we round off, don't you? If you round this off, if you add these and you round off, right, to where you should, what's this? This comes out to, like, that's a zero. That comes out to what? Zero. Doesn't contribute. Does everyone follow now? Because you've done that. You've aligned the decimals. Does everyone see it now? These are the concepts you've been learning already. So now when you see them, you kind of go, oh, got it. That's what we want you to do, okay? These are the concepts. So you say, that's outside the nucleus, no real contribution to mass. We just don't look at it, okay? To the atomic mass unit, okay? All right? From which we do derive what we call the mass number, okay? But don't confuse it with the number on the periodic table. Got it? It's going to be a whole number. So this is what we've been reading off the periodic table. The atomic number, chemical symbol. Atom, the atom of an element is electronically neutral. Everything on the periodic table is neutral. And in this class, we're only going to deal with neutrals, which means that you have the same number of protons and electrons. Now you see why that's the case, right? So you can add as many neutrons as you want. It won't change the electronic charge of it. It just simply changes the mass of it, which is its isotope, meaning it has more than one mass. But will the number of protons change? No. Got it? Carbon is always the same. We've gone through these. We've done this in the math session. So we just pointed out to you again. We went through this in the math session. Now you get it? Does everyone see it? This is what you've already done. This is what you already know how to do. We just did this, didn't we? You get it? So this slide, atomic symbols, particles, here they are. No changes there. Another example, carbon. You guys know how to do this. We've done it already. So I'm not going to belabor that. Here, this is the atomic mass, but this is not the mass number. Keep that in mind. Does everyone follow? This is not the number we use for the calculations. Okay? This is a small whole number. We've already talked through that. Isotopes are what we were just telling you about, right? Isotopes change where? Protons, neutrons, electrons. Neutrons. Can you have more than one neutron number? And that's called isotope. That's what we show you here. Lithium has, okay, this is lithium. I don't like the way you show it. I'm trying to do this without sharing my pet peeve on this. I don't like the way the author changed a few things and organized a few things. Okay, I'm over it now. I vented. Okay? I would have preferred that he kept the atomic numbers at the top, which is what he did on the previous pages. You got it? But he didn't. Does everyone see that? So don't confuse the two. You notice he dropped his atomic number to the bottom? You know how I know that's atomic number? It didn't change. Because atomic numbers do not change. If you just, from what I just showed you in the last slide, remember where you had it? And then he flipped on you? Watch for that. He does that a few times in his book. Yes, I've already written my letters to him several times. He ignores me. You get it? You know your atomic numbers because they don't change. I've already taught you that in the math sessions. So here, but notice here, these are the mass numbers. He put his mass numbers now at the top. Here, be aware of that. So why is this mass number change? It's called what? Isotope. What are the number of neutrons in this first isotope? Neutrons. 3. Right, 3 neutrons, right? You got it? You know why 3, right? You got to subtract it. How many neutrons in this one?
4.
Now you see why? That's called an isotopic effect. Let's do this one. How many neutrons?
6.
How many here?
7. 8.
You getting it now?
8. 9. 10.
These are called isotopic effects. So the true carbon or true oxygen, true fluorine is a combination of all these isotopic effects, which is where we get the number that goes on the periodic table. We get the number on the periodic table from its isotopic effects. In this class, you will not be required to learn how to do that math in detail. You will be required, however, to know what that math looks like, and I'm going to show you that in another session, another math session, okay? All right? Based on what we've in the curriculum here and in the syllabus, that's not part of what's required to know how to get to it, but to recognize it. And you now recognize that when you see this number is a combination of these numbers in percentages. Does everyone follow me? Okay. Here, we've already done this, right? You know how to get all of these down, don't you? This is the mass of the isotopes. This I'm going to show you in another math session how to do and what it looks like. Okay? It's based upon these percentages. And here it shows you how we walk through that math, but we're going to do this in detail in another session, math session when we have it. And this shows you how we do it. So let's just show you here in a nutshell. This is isotope what? 24, isotope 25, 26. How many protons in magnesium? Where would you get it from?
12.
12? Okay, I'll take your word for it. For the magnesium?
Oh, magnesium?
Where'd you get it from?
Well, from the periodic table.
Yep, so look at a periodic table. Somebody give it a number. Oh, okay, I'll take your word for it.
Well, isn't that right there?
I don't know.
Oh.
Does everyone get the point? I'm trying to make sure you're looking. Does everyone I'm sorry, I like to do that to you. I'm trying to make sure you're calling it, you're seeing it. You got it? Okay, because sometimes when I get to talking, I'll keep talking, everybody. Okay, so you're saying, isn't that it? Okay.
Yes.
Does everyone see what he just did now? He flipped again on us. Right? He put them back at the top. I hate him doing that. Okay, I'm over it. So it's 12. Okay, take your word for it. 12. So now, how many electrons in this, by the way?
12.
Okay. How many neutrons in?
That one is 12.
Okay. How many neutrons here?
13.
How many here?
14.
Okay. And so when we do what they found, the scientists found was this isotope was about 79%. This isotope was about 10. This isotope was about 10. When they run the math, it comes out that this is the atomic mass number, which we also call the molar mass. Okay, which is gram per mole. You're going to see those interchanged. These are the trends in the periodic table. Bear with me for just a minute more, okay? I'd like for you to really study this and take a look at it, okay? And what would I like for you to know when you come back? These blocks. This is one example. If you look in your book to find them. These are called the S. This is called the S block. These are like block city blocks. These are districts. You get it? Okay, it's like the downtown district, midtown district, and the mall area. And you have the addresses. So this is located in what? The S block at what? 2, 2. Does everyone follow what I just did? So this is the S block, P block. We always go S, P, D, F. S block, P block, D block, F block. Each of these blocks tells us something about the characteristics of the chemistry. Okay, and so you think of these as districts. So this is a matter of memorizing which district they're in, which region of town they're in. Don't look at it any different than that. These are addresses. That's how we look at the periodic table. There you have it. You have now survived Chapter 4.